Chapter 15, Chemical Equilibrium. This chapter tends to be fairly easy for our Chem 2 students. If you find this chapter easy, please take a little extra time, work a couple more of problems out of section 15.5, calculating equilibrium concentrations, as well as relating chemical equilibrium to free energy. This chapter is the foundation for the next 2 units, so make sure you have a nice firm foundation here. If you've worked those problems and you still find this to be an easy chapter, then move on to the next one because you never know what's coming down the pike you might need a couple extra days with. So we were going to be talking about equilibrium and all the calculations involved with equilibriums. Now, most reactions are not discrete reactants that then form discrete products. We tend to have reactions that stop when there's a particular mixture of reactants and products. And we show that with this type of reaction arrow. We have half going one way and half going the other. That is called an equilibrium mixture. So we have a forward reaction going from left to right, that's forward, and we have a reverse reaction or a reversible process. So that means the products can form the reactants, as well as the reactants forming the products in the traditional manner. So it is an equilibrium when the rate of the forward reaction and the reverse reaction are the same. Now we haven't done reaction rates yet, but know that an equilibrium occurs when your forward reaction equals your reverse reaction. So here we have as an example the decomposition of dinitrogen tetroxide. Dinitrogen tetroxide as a gas, and it is going to decompose into nitrogen dioxide. That is also a gas. Now, nitrogen dioxide is brown. Okay, so this is brown, and this is clear. I can't spell clear. So we start with our reactant that's clear, and over time, our reactants diminish. Here's our reactants diminishing. So the colorless diminishes as the brown increases, and over time we get to what's effectively a steady state. We're not making any more reactants than we are products. Now products is a little bit favored over here. We have a few more products than we do reactants. But we've reached an equilibrium. We have reached a state where the concentration of the formation of products, the concentration of the products does not change, nor does the concentration of the reactants. Now, if we were to take this in reverse, so this was our forward reaction. This is what we showed on the previous slide. Now we're going to start with our NO2 as our reactant. And we're going to form our product, dinitrogen tetroxide. So we flip-flopped. This is the reverse reaction. So initially, only NO2 is present. So initially, we only have brown. Now, only the reverse reaction. So only NO2 recombining to form N2O4 is occurring. Therefore, we will form a more colorless solution. And here again, we have formed a steady state, an equilibrium where the concentration does not change. Generally speaking, an equilibrium is a fairly easy thing to conceptualize. You've got this steady state. Now, equilibrium is dynamic though, so don't get lulled into thinking that this is static. Both forward and reverse reactions do continue to occur, but there is no net change. It's kind of like a seesaw on the playground. If the children can balance just right, then that seesaw appears to be static. But really, both children are working pretty hard to keep this seesaw static. Now, an equilibrium can be established starting with only reactants, or with only products, or with any mixture of reactants and products. Now, you know we have to get to math here because this course is math-based. Chemistry and math are married. We will not separate them. So when we talk about an equilibrium, we can talk about it in terms of the reaction quotient, or the Q. That is a fraction of product concentrations and reactant concentrations. Each concentration will be raised to a power equal to the stoichiometric coefficient of the balanced chemical equation. All of those words mean our Q, our reaction quotient, will be equal to the concentration of each of the product of each of our products raised to the power of the coefficient here, that's what this is here, divided by the concentration of each of our reactants raised to its appropriate coefficient. And that ends up being equal to a constant Kc. K is the important function here, and we will be using a lot of K values over the next several units. Kc indicates that this is a concentration. We're looking at molar values. Now, this is what's called the law of mass action, and it applies not only to elementary reactions, but also complex ones as well. So if we're going to write reaction quotients for each of the following reactions, when we're writing a quotient, it's called Q. So I'm going to take the concentration of my product raised to the appropriate coefficient here, divided by the product of my reactants raised to their appropriate coefficients like this. So this is the reaction quotient for A. I'm going to write B over here. B, the reaction quotient, is equal to the concentration of the product raised to the power of the coefficient from the balanced chemical equation divided by the concentration of each of the reactants multiplied together. So for C, I have my Q value is equal to the concentration of my product divided by the concentration of each of my reactants. But in this case, the ammonia is raised to the second power because of that coefficient. That's what that is for. For C, C is a little bit easier, but don't get misled here. We have our product raised to the third power. We have our reactant, I put a Q. We have our reactant raised to the second power. Don't get confused by where the 2's and the 3's go. For E, we have no coefficient, so we don't raise it to a power. But for the bromine, that gets raised to the fourth power because the 4 is the coefficient. And for F, product, reactant. So now we're going to use that equilibrium constant, that quotient. So the QC is equal to Kc. Typically, you're going to see it as a K value. So we can write this for any point during the progress of the reaction if we know some of our concentrations. Now look at the relationship here. We have our product, we have our reactant. So if we're going to get the value of the reaction quotient Q for any particular point during the reaction, as the reaction progresses, that's going to change because the concentrations will change. Now, when you divide a number by 0, you can't really do that. So your book's going to define that as being an infinite number. So we're going to ignore the initial point here. But when you get to a point where, say, each of the concentrations are the same, your reaction quotient doesn't necessarily equal 1 because of these coefficients. This is most easily shown by working a problem. So if we have carbonyl chloride, which is also called phosgene, and it's a highly poisonous gas, and it's produced by this reaction. In an experiment conducted at 74 degrees Celsius, the equilibrium concentrations are given here. We need to A, write the equilibrium expression, and B, determine the value of the equilibrium constant. So the equilibrium expression is going to be the concentration of the reactants divided by the product of the concentration of, I think I said reactants there. We have the concentration of the product divided by the product of the concentration of the reactants. Too many products and reactants. So this is your equilibrium expression. So now we're going to plug in our values appropriately and get the value of Kc. The fact that it's at 74 degrees Celsius really isn't relevant. As long as the experiment is conducted at one temperature, the temperature doesn't matter to us all that much. It doesn't come into play with this type of calculation. So first I'm going to enter the concentration of my product, and then the concentration of each of my reactants. Because I do not have anything raised to a power, really doesn't matter what order they go in, but I will do them like this. Everything is in molarity, so when I do that arithmetic, I get 216, but I need to be careful with my significant figures. If you don't recall significant figures, please review chapter 1 of your book. So significant figures, I have 2 sig figs in each of the values used for my calculation. Remember, the 74 is not used in my calculation, so I need to report this as 2 significant figures. I could say it's approximately 220, that is 2 significant figures, but this is ambiguous. So in order to avoid any ambiguity, I would report this as 2.2 times 10 squared equals my Kc. Now we can calculate the equilibrium constant, but really what good is it? Well, it tells us to what extent a reaction will proceed at a particular temperature. So we have 3 potential outcomes. Either the reaction will go essentially to completion, and the equilibrium mixture will be predominantly products. That will occur with a very, very large Kc. So if K is much, much greater than 1, then we have primarily products. And that makes sense because our K is a ratio of products to reactants. So if we have many more products than reactants, we have gone essentially to completion, and our K value shows that being a large number. We can have a reaction that does not occur to any significant degree. So we have primarily reactants. And when we do that, we have a very, very small Kc. So the K will be much, much less than 1. Or we can have a reaction that proceeds but will not go to completion. And that particular equilibrium mixture contains comparable amounts of both reactants and products. So that is where Kc is approximately equal to 1. Now these equilibrium expressions are very easy to write when everything is aqueous. But what if we have species of different phases? Well, then it's called a heterogeneous equilibrium. Only gaseous and aqueous species, this is very important, only the gaseous and aqueous species will appear in an equilibrium expression. So if you have a pure solid and a pure liquid, they will not appear. So for example, in this equilibrium expression, we don't count the concentration of the solid carbon, because as long as there's solid carbon, there's solid carbon. It doesn't have a concentration to measure. So we keep the gases in our Kc. For this particular reaction, it would only be dependent on the amount of hydrogen gas, because water as a pure liquid doesn't have a concentration that we can calculate with, and these are solids. They don't have a concentration we can calculate with either. So the equilibrium expression is purely dependent on the amount of hydrogen gas in the system. So if we're going to write equilibrium expressions for each of these reactions, then now you have to pay attention to the phases. So for example, for A, the equilibrium product, K, is only dependent on the concentration of carbon dioxide. For B, we have liquid mercury. That doesn't count, so the K is going to be dependent on the mercury 1. Remember, mercury 1 is a diatomic ion. There we go. And mercury 2. For C, we don't count the solids or the liquids, so the K is purely dependent on the concentration of hydrogen gas squared. And for D, we don't have any product to speak of. So in this case, it would be 1 over the product of the reactants, the mathematical product. We can manipulate equilibrium expressions if you reverse the chemical reaction. If we go from A plus B reacts to form C and we have one set of, or one constant, then if we flip-flop it and have the C be the reactant, then we have to take the reciprocal of our product constant. So, and that it makes sense because instead of having the product here, C, now we have our C is on the bottom because it is a reactant instead of a product. So it is the reciprocal. Remember reciprocal, if you have a reciprocal button on your calculator, it probably looks something like that. Or maybe it's x to the -1. Either way, I've had calculators that have both of them, but that is your reciprocal. If these two reactions have these indicated equilibrium constants, and all that we need to know with the temperature is that it is constant here. We don't need to use the temperature in our calculations. We are asked to determine the value of Kc for each of these reactions. Well, first thing I'm going to do is write out what my equilibrium constant expression is, so that then I can compare and see what the relationship is, and then that will help me determine what I need to do with this number. So this is the equilibrium expression for this reaction, and this reaction looks like this. So for A, the equilibrium constant expression, I'm using number 1 to compare. So I'm going to write, I don't want to call it Ka, just the K looks like this. And it appears to be the reciprocal of what I'm given, of my number 1. And because it is the reciprocal of my Kc, I'm going to take the reciprocal of this number here, and I get, since that's the reciprocal, so if I take 1 over 0.014, I get my Kc value is 71. For B, I'm going to do the same thing. And to save a little time, I just wrote out all of the equilibrium expressions here. Now B, when I'm looking at the difference between B and my original equation up here, number 1, I can see that the reaction is actually multiplied by 2. And since the reaction is multiplied by 2, then my equilibrium product constant here is squared. So what I need to do mathematically is then square the number. So I have 0.014 squared, which equals my new Kc, which in this case is going to be 2.0 times 10 to the -4th. Now for C, I'm multiplying this equation by 1/2, and in order to multiply it by 1/2, then when I look at the Kc expression, that's actually the square root. So mathematically, I need the square root of this number, and I get 0.1, nope, yeah, 1, 2. Now for D, this is actually the addition of these two equations. I'm adding these two together. And the equilibrium expression then is a product of two individual expressions. I've multiplied these two together. The bromines actually cancel out, which is why you don't have 3 variables in the numerator as well as the denominator, because the bromines actually cancel out. So in this case, if we're going to add our reactions together, we actually multiply our numbers together, our Kc's. So it's 0.014 times 7.2. And I get a value of 0.10 for my Kc for D. For E, we have the reverse of D. Here we have our products, reactants, but we've also multiplied it by 1/2. If you multiply the coefficients by 1/2, you're taking the square root of the Kc. So not only am I going to take the reciprocal of what I get in D, I'm also going to take the square root of it. And that is equal to 3.2. So this is all about manipulating these numbers in order to make sense. When we only have gases in our equilibrium, we can write an alternate form of the expression, and that is based on the partial pressure of the gases in our system. So for example, if our concentrations look like this, then our partial pressures are built similarly. So we have Kc for concentration and Kp for pressure. It's just the partial pressure of each of our constituents or our compounds raised to the appropriate power, just like with the concentration, just talking about pressures now. Now the relationship between Kc and Kp though, you have to bring in the gas constant, and this is where it's important to know the temperature. Please understand, write down, and know how to work this expression. Kp is equal to Kc times R times RT. This RT is raised to the power of delta N. Delta N is the difference in the moles of the gas in the products and the moles of the gas in the reactants. So for this particular example here, the Kp is going to be equal to the Kc times R times T, which we're not given, raised to 1, the first power. So we're not actually raising it to a power because the delta N is the number of moles in the products 2 minus 1. Remember, not putting a number here is a 1, not a 0. So for example, let's write Kp expressions for these equations. So for A, my Kp is going to be the partial pressure of PCl5 divided by the pressure of PCl3 times the pressure of Cl2. For B, remember, the liquid does not enter, so Kp is going to be 1 over the pressure of oxygen times the pressure of hydrogen squared. And for C, I'm going to have my Kp is equal to the pressure of HF squared divided by the pressure of F2 times the pressure of H2. So now let's use that Kc-Kp relationship in this problem. The equilibrium constant Kc for this reaction is given to us here at this temperature. So what's the value of Kp? Well, remember that Kp equals Kc times RT raised to the delta N. Well, Kc is given to us at 4.63 times 10 to the negative 23. And then we have our RT term. Now our RT term is going to be raised to the delta N. In this case, delta N is 2 minus 1, which is 1. So I really just need my R, and that is liters, atmospheres, mole, Kelvin, times temperature. Now the temperature is given to us in Celsius, but remember we need to convert that to Kelvin. If you don't remember that you need to convert that to Kelvin, please look at the units given for your R value, and that will tell you. So that's 298 Kelvin. So multiplying all of these numbers together, I get a value of 0.113 for my Kp. Now K can tell us a little bit of information about our delta G. Remember, delta G is the Gibbs free energy, and we covered that in the previous unit in the previous chapter. So if our K is much, much greater than 1, so if K is really favoring the products, remember this is a reaction that goes just about to completion, then we have a negative delta G. Remember, this is a spontaneous there we go, spontaneous process. A negative delta G is spontaneous. A reaction with a K value much, much smaller than 1 has a positive delta G. That is non-spontaneous. The magnitude of K and the sign of delta G will help us to solve some problems. Now also remember the difference between Q and K. Q is going to be at any one moment. So we're going to know our concentrations there. And K is the general constant, the value given. So we have three possibilities when we're looking at a comparison between QC and KC. If Q is less than K, then the initial concentrations of the products or reactants is too small. And in order to reach equilibrium, the reactants must be converted to more products. So the system will proceed in the forward direction. If Q is equal to K, then that means the initial concentrations are the equilibrium concentrations. So we are at equilibrium if Q is equal to K. If Q is greater than K, though, the ratio of initial concentrations to products to reactants is too large. So the reaction is going to proceed towards making more reactants in order to bring that Q back to K. Q equaling K is equilibrium. So we want to bring Q back to K. So for example, if we're going to work a problem like this, we're asked to determine whether the system is at equilibrium, and if not, determine which direction it must proceed. So what we need to do is calculate Q. So to do that, I have, okay, so the equilibrium constant for the reaction is 1.2. So I am told that K equals 1.2. Now let's calculate Q. I'm going to set it up as a concentration here of, yeah, I'm working concentrations because I'm given concentrations here. So the concentration of ammonia squared divided by the concentration of nitrogen times the concentration of hydrogen cubed. So I'm going to plug in my numbers. Now you also have to understand what the word respectively means. We're told nitrogen, hydrogen, then ammonia. So this is nitrogen, this is hydrogen, this is ammonia. So I can plug in my numbers appropriately. And I'm going to leave the capital M molar off here. And this is cubed. And when I work that number, I get a Q value of 0.61. Now Q is less than K. So that means, looking back, Q is less than K, then the ratio of my initial products to reactants is too small. So I need to convert more reactants into products. So this will proceed in the forward direction, or to the right. Now it's the sign of delta G, not of delta G naught, that will determine our spontaneity. Delta G is going to be calculated from thermodynamic data. Okay, so this is where you go to appendix, not B2 for this book. But delta G is what we're looking for in order to determine our spontaneity. And that's based on our delta G naught, which we calculate, and of course, something that has to do with equilibrium. So our R is our gas constant. T is our temperature in Kelvin, and then we have the natural log of Q, the quotient at that particular time. Now here our gas constant is going to be the joules version because we're working with energies now. So it's the 8.314 joules per K mole. T is the Kelvin temperature. Remember your relationship between Celsius and Kelvin. So Kelvin is equal to Celsius plus, for most things, we just use the 273. Sometimes we use 273.15. You shouldn't end up with a problem that is that picky that you have to use one versus the other. So you can do these calculations with 273 and get the adequate precision to your answers. If you come up with something that does not show that adequate precision, I want to know about it. So send me an email with the quiz problem. Now Q is the reaction quotient as we have been calculating in this chapter so far. So if we're going to consider this particular equilibrium, and the delta G naught we find to be 2.60 kilojoules per mole, and you can actually calculate that from the values in Appendix 2. Remember how to do that with last unit's information. Delta G, which is what we're going to find for spontaneity, is going to depend on the partial pressures of each of these chemical species. So if we have these partial pressures, then we can find the quotient, and the quotient here is going to be 2.25. So we plug in all of our numbers. Now delta G equals, and this is our delta G naught plus R times T times the natural log of Q. And when we get that, when we plug in all those numbers and we do that calculation, then our delta G number is a positive 4.60 kilojoules per mole. Now that tells us that this is a non-spontaneous reaction at 25 degrees Celsius and these pressures. Now we can change the spontaneity by changing the partial pressures of the reaction components. So if we have different partial pressure values, we will get a different Q. With a different Q, this is the same equation, so this is our G naught, it's the same G naught, it hasn't changed, R hasn't changed, T hasn't changed, but Q has. By changing the partial pressures of our reaction components, we can then form a spontaneous mixture. So the concentration of the reactants and products is very important in determining whether a situation, a chemical reaction, will be spontaneous. Now in this case, we have an equilibrium constant Kp for this reaction, and that equals, here we go, I'll write it up here, Kp equals 0.113. Now I'm given my T value of 298 K, and that corresponds to a free energy change. So my delta G naught, I'm told, is 5.4 kilojoules per mole. So we have our initial pressures here, so I can calculate my Q value, and Q is going to be P of NO2 squared divided by P of N2O4, and I'm just looking up here for that. So I can calculate based on those numbers. So I can get my Q value then for this particular reaction is 0.0329. And then I can calculate my delta G. Remember, delta G equals delta G naught, given to me right here, plus R times T times the natural log of Q. So now I'm going to plug in all of my values. 5.4, and that's kilojoules per mole, plus my R value, 0.0, nope, not 0.82, 8.314 joules per K mole, times my temperature in Kelvin given to me, times the natural log of my Q value I just calculated. So all of that arithmetic mushes all together, and I get, and I'll do it in steps for those of you who might be a little foggy, 5.4, and that's kilojoules per mole. And then I actually get a negative value, a negative 8.46, and that's again kilojoules per mole because these kelvins cancel out. And then again, I, just like in the last chapter, I automatically convert between joules and kilojoules to match my units. And I would strongly recommend that you do that as well. If you need to take the time to do the extra step, please take the time. So my delta G in this case is a negative 3.1, and that's kilojoules per mole. So this is a spontaneous process. Now we've defined equilibrium as the condition where the reverse and the forward reactions are occurring at the same rate, but no net reaction is occurring in either direction. So the concentrations of the reactants and the products are constant. We've seen that in a couple of the previous tables or graphs that we have shown. So in this state, Q equals K. So when we are at equilibrium, Q equals K and delta G equals 0. So when we take our delta G equals delta G naught plus RT ln Q, we substitute K in for Q, and our delta G is 0, then what we get when we rearrange is that delta G naught equals negative RT natural log of K. And you can probably see where this is going since we can calculate this from thermodynamic data. Now remember the relationships between K and delta G naught, as predicted by this particular equation. When K is greater than 1, the natural log of K is positive. Delta G naught is negative, so products are favored. Products are favored when your K is greater than 1. At equilibrium, K is 1, so the natural log of K is 0, and therefore delta G naught is 0. Neither products nor reactants will be favored. When K is less than 1, ln is a negative number, and that makes delta G naught a positive, because if this is a negative number, and a negative number times a negative number is a positive number. So in that situation, the reactants will be favored. So if we use data from Appendix 2 and we calculate the equilibrium constant Kp for this following reaction, well, how are we going to do that? Well, we're going to start by calculating delta G naught. Remember, delta G naught is going to be the sum of the products. So this is the G of the products minus the sum of the G of the reactants. So I look up all these values in Appendix 2, and what I'm looking for is the delta G of H2, which I find to be 0 kilojoules per mole. Now remember that the G, the Gibbs free energy of an element in its most stable state, is going to be 0. Well, that happens to be this as well. The G of oxygen gas is 0. So then I'm going to subtract the Gibbs energy that I look up for liquid water, and it's 2 times the liquid water because we have a 2 for our coefficient here. So I have 2 times a negative 237.2, and that's kilojoules per mole. Now we have a negative and a negative. So what I'm going to end up with is a positive 474.4 kilojoules per mole. Now I'm going to use this value in this equation. So my delta G naught equals negative RT natural log of K. What I'm looking for is K. So I have my delta G naught of 474.4, and I'm going to use kilojoules per mole. Now keep track of your joules and kilojoules. You need the gas constant R, but in this case we need a negative 8.314, and that is joules K mole. You're going to need to convert that into kilojoules so that our units match. Multiply it by the temperature. The temperature is given to us at 25 degrees Celsius. That is 298 K. And then I have the ln of K. So I work all this out and I get a negative 191.5 equals the natural log of Kp. Kp is what we're looking for. Now you have to take the inverse log. On some calculators, it's an e to the x button. On some calculators, it'll be shift or second and then the ln button. I don't know what your calculator looks like, so I don't know what buttons you will have to push in order to get this to work. But the inverse log of Kp makes Kp equal, I get 7 times 10, I think that's negative 84. So work your calculator until you get this number as well, or something really, really close to it so you can round it to make 7 times 10 to the negative 84. Now this is a really small number. So K is much, much smaller than 1. And what that shows us is that then we have a positive value of delta G will be greater than 1. My G's are starting to look like 6s. These two situations, having your K much smaller than 1 and your delta G naught much greater than 1, shows us that this is not a spontaneous process. And we know that because at room temperature, water just does not spontaneously decompose into hydrogen and oxygen gases. If we have this equilibrium constant for the dissolution of silver chloride in water is 1.6 times 10 to the negative 10. Now this is called a solubility product, KSP, and that's what the subscripts after the K's show us. The K gives us that it's a product of products over reactants, but in this case, our only reactant is a solid, so it's only based on the concentration of our products themselves. But we are told that K is 1.6 times 10 to the negative 10. And we're asked to calculate delta G naught. Now remember, delta G naught is a negative RT ln K. I'm going to plug my K in here. My R is going to be 8.314 times 10 to the negative third kilojoules per K mole. My temperature is 298 Kelvin. And then I need the natural log of 1.6 times 10 to the negative 10. Make sure you are using the ln button, not the log button. ln, natural log. So I get my delta G naught value, when I multiply these together, is 55.9 kilojoules per mole. Now this is a large positive delta G value. It's much greater than 1. And like the really small K value, this gives us a process that lies far to the left, which means this favors the reactants. There's going to be more solid silver than there will be ions of silver chloride. So now that we can manipulate our Ks, we can calculate Qs, we can calculate the free energy and see if things are spontaneous or not. Now we're going to get to the part that the next couple of units will build on, and that is calculating equilibrium concentrations. So the equilibrium expression can be used to predict the direction of the reaction and to calculate those equilibrium concentrations. And we make those predictions based on Q and K. So if Q is less than K, and this should be a review from earlier in this chapter, if Q is less than K, more reactants must be converted into products, because currently our reactants are favored. If Q equals K, then the concentrations are equal and we are at equilibrium. Then the concentrations are our equilibrium concentrations. That's what I'm trying to say. If Q is greater than K, however, then our products are favored. We have too many products, so they need to be converted into reactants. We've pushed past the equilibrium concentration. Now, the equilibrium concentration can be calculated from initial concentrations if we know the equilibrium constant. So if we know Kc is a value of 24, we also know, and remember, this temperature here doesn't necessarily come into play when we're doing these calculations, only when we're looking at our delta G's in relation to K's. So I'm looking at Kc equals 24. Maybe it would be easier if I went this way. And I have the concentration of my products divided by the concentration of my reactants. So if I have my initial concentration of my reactant, because this is what I'm starting with, and I'm going to establish this equilibrium, then I will change the concentration by some value x. I'm going to remove that amount, some amount x, of my reactant. When I remove that amount of reactant, I'm actually adding that amount of product. Remember, I'm working with moles. My initial concentration is moles per liter, and since my volume is not changing, I can look at this as a mole transfer. So however many moles of my reactants I take away, I'm adding that many moles of my products. So my equilibrium concentration will then be 0.850, my initial concentration, minus x, and then x will be my equilibrium concentration of my products. Now I can then plug that in. So my Kc equals the concentration of the products divided by the concentration of the reactants, and that all equals 24. So the concentration of my products now in terms of variables is x over 0.850 minus x. So now I have this one equation and I have this one variable x that I need to solve for. Now, x represents the change in initial concentrations, okay? So we still need to solve this. Now, you might want to review your order of operations and how to mix this up in order to solve 4x. Just to work this out briefly, for those of you who may need a refresher, I need to multiply both sides by my denominator. And what that's going to give me, I'm going to try to write this down as quickly and neatly as I can. That would give us this term. So now I need to distribute my 24 through this part of my equation. And what I get, 24 times 0.85, I get 20.40 minus 24x equals x. Now I need to combine my x terms. So 20.40, I'm going to add 24x to both sides. In order to do that, I get 25x. Now to solve for x, I need to divide both sides by 25. And when I do that, I get x equals 0.816 capital M molar. Now that is the change in initial concentrations. So now I go back up to my table, and this is called an ICE table, initial change equilibrium, ICE. So here my change is 0.816 molar. So my equilibrium concentration of my product is 0.816, but I need to subtract 0.816 here. And then I get, let's see, that would be 4.3. My equilibrium concentration of my product, or my reactant, then is 0.034 molar. So that's how we calculate equilibrium concentrations. So to work another example, if we're given the Kc of a reaction of hydrogen and iodine to produce hydrogen iodide, and we're given that Kc equals 54.3. Now the equilibrium expression, from that equilibrium expression, I know I have Hi squared divided by the concentration of hydrogen gas times the concentration of my iodine gas. What will be the concentrations at equilibrium if we start with 0.240 molar concentration of both of my reactants? Well, I'm going to write down my reaction here. And so my initial concentration is my 0.240. My change is going to be some value x. But because I have this 2 here, that's going to be 2x that I'm changing it into. Then at equilibrium, I have 0.240 minus x for each of my reactants, and then 2x for my product. So then I can plug that in. So I end up with 2x squared divided by 0.240 minus x, 0.240 minus x. Now this becomes an easier expression to solve if you recognize then that what I have is 2x over 0.240 minus x squared. So I can take the square root of both sides, and when I take the square root of both sides, I get 7.36, and I have more digits here, I'm just going to leave them in my calculator, is equal to this expression. Now I'm going to multiply both sides by my denominator, and when I do that, and again I have left this number here, I have left that in my calculator, so I don't have as much rounding error, but I get 1.768, and then I have more digits, 5 something else, minus 7.368x equals 2x. Now I need to combine my x terms. And to do that, I need to add 7.368 to both sides. So I get 9.368x equals 1.768 and more numbers. Divide both sides by this 9.368 stuff. And I get x equals 0.18878. And I have too many digits here on purpose. Now I'm going to go back to the question. The question asks, what will the concentrations be at equilibrium if we start with this amount? Well, this is how much we change. And here is my x. So now I need to plug in this number, 0.18878 number, into these parts right here in order to solve for the equilibrium concentration. Now, because we have 3 digits past the decimal here, I'm only going to retain 3 digits past the decimal here. So I'm going to round this to 9. There we are. And so I subtract from 0.240, I subtract 0.189, and I have an equilibrium concentration of hydrogen is 0.051, and that is also the equilibrium concentration of my iodine. Now, the concentration of HI, however, is 2 times 0.189, so the concentration of HI equals 0.378. Now, all of these are capital M molar. If we use the same reaction we just worked with, what are the equilibrium concentrations if we start with these values? Well, the first thing I need to do is figure out what my Q is. Where are we in the equilibrium? Are we going to be adding products or are we going to be adding reactants when we start changing? So remember that the equilibrium expression was based on HI squared times H2 times I2. So then put your numbers in and calculate. So you need to square the 0.0424 and then divide by the product of these numbers. And I get a Q value of 69.7. Since Q is greater than K, remember my K, I'll write it up here, I guess. K was 54.3 if I'm not mistaken. Yes, 54.3. So because Q is greater than K, that means we have too many products and we will be adding to our reactants. We will be removing products. Okay, and the reason we need to know that is because when we start putting in our ICE table, initial, change, equilibrium, that determines the sign of our change. So we're going to start with our initial conditions given in the problem. And now when we change, we're going to remove product and add, I'm going to give it the same stoichiometry, and add reactant. So our equilibrium concentrations then end up looking, like this. So we're still calculating the change in concentration. It's just in this case, we're removing product because the Q value was much larger than the K value. So now when we plug this business into our K, we get something like this. Now, this isn't one of those really clean, easy to solve kind of problems. We have to take part in all of the calculations now. We have to multiply everything through and get all of our terms. And so we end up with this expression. Now you have to use the quadratic formula. If you don't remember the quadratic formula, we will give it to you in the book. It won't be given to you on an exam. Now we have to use the quadratic formula in Appendix A, and here it is. Write it down and keep it near you, and I'll tell you when you can make it a little easier. So you have to know that your A term goes with your x squared, your B term goes with your x, and your C term is the number all by itself. Plug it into the quadratic formula. Please use your calculator. Know how to use your calculator appropriately. And we get these two values, the 5.25 times 10 to the negative 4, and we also get a negative 0.01 0.0151. Now this negative value just doesn't make sense because we can't change, our concentration isn't going to be negative. So we can only use this value when we go to calculate our equilibrium values. So we put it back into our equilibrium expression. We have our initial here, our initial concentration 0.00625, and we're going to add our 5.25 times 10 to the negative 4, so we have an equilibrium value of 0.00676 molar. Now our I2 concentration at equilibrium will be different because we started with a different value. And then our HI, again subtracting 2x in order to make the stoichiometry make sense, and we bring that down to a concentration of 0.0414. You can check your work by then putting the equilibrium values into your K expression and double checking to make sure that you actually do calculate to get your reported Kc. For this problem, we have a mixture of hydrogen gas and iodine gas again to produce our product. We have a 1 liter vessel at this temperature. So we have our Kp for the reaction at 54.3. We are asked to determine the equilibrium partial pressures. We handle this the very same way. We have our initial pressure of hydrogen, there it is, 5.75. That will have a change. Our iodine is also 5.75, and that will have a change, but we have no product yet. So that will have a positive change of 2x. So our equilibrium pressure will be 5.75 minus some amount x. And this is a stoichiometric amount. Now I can put that into the Kp expression, 5.3 or 54.3 equals the partial pressure of Hi squared, 5.75 minus x, 5.75 minus x. Now this is another one of those that works out so very nicely because all we need to do is take the square root of both sides. And when I get the square root of both sides, I believe that was 7.369. And that is equal to 2x over 5.75 minus x. Go through the algebra here and end up with 42.37 equals 9.369x. Solve for x and get a change in this case of 4.52 atmospheres. Then to solve for the pressures, the pressure of hydrogen will also be the pressure of iodine. So you start with 5.75 and remove 4.52 to get the equilibrium pressure of 1.23 atmospheres of each of those. And then the pressure of your product would be 9.04 atmospheres, or 2 times our x value, as indicated right here. Before we really dive into Le Chatelier's principle, I want to point out that not everything will be neat and tidy and a squared function you can just take the square root of when you're calculating equilibrium concentrations. When we work through some of the problem solving in the clicker questions as well as the end of chapter questions, I will point out where you can simplify that. And it all has to do with the relationship between the initial concentrations and the K value. You're looking for 3 orders of magnitude different. If this is brand new to you, I will lead you through it in the problem solving specifically. If we were on ground, that would be a second day's worth of information. So in one day we would present this information, and on the second day we would work problems. But Le Chatelier's principle and factors that are going to affect chemical equilibrium. So this principle states that when an equilibrium is stressed, the system will respond by shifting to minimize that stress. So a stress can be the addition of a reactant or a product, the removal of a reactant or a product, or a change in the volume of the system if we're looking at gases. or something that results in the change in the concentration. We can also change the temperature. That can also shift in equilibrium. Now, for example, we have what is called the Haber process. The Haber process is a long established way to produce ammonia. And at equilibrium, the nitrogen concentration equals 2.05 molar, and the hydrogen concentration is 1.56 molar, and the ammonia concentration is 1.52. Well, because this is a process that we're trying to form ammonia, we will end up removing some of that ammonia. Well, the first example, if we add nitrogen in order to change the concentrations, then we have to adjust the other concentrations in order to keep the Kc constant. So the reaction will, it's called shift to the right. If we add nitrogen, we will shift the equilibrium towards the production of products, shift it to the right towards the production of products in order to remove that stress, in order to remove the addition of the nitrogen. Now remember, we're looking for equilibrium. We're looking for where the concentration doesn't change. So here we have our first equilibrium, equilibrium number 1. We have stressed it by adding this amount of nitrogen, and in doing so, the production of ammonia was increased, but we have less hydrogen because we didn't add additional hydrogen as well, until we form a second steady state. So if we add any of our reactants, or if we remove ammonia, this is a process to make ammonia. So if we remove that ammonia, we will shift the reaction to the right, towards the production of more products. If we add a product or remove a reactant, we will end up shifting the equilibrium towards the left. If we add more product, we have to shift away from that addition in order to alleviate that stress. If we remove one of our reactants, then our product will answer that call by shifting towards the production of more reactants in order to alleviate that stress. So for each of these scenarios, if we're to determine if the equilibrium will shift to the right, left, or neither, if we have something like the addition of oxygen, so we're adding here, we will shift away from an addition. So A will be shifting to the right. For B, if we're going to remove hydrogen sulfide, so we're taking this out, we will shift towards a removal. So this will shift to the left. For C, if we're going to remove water, we're going to remove steam, basically, we will shift towards a removal in order to alleviate that stress. That's to the right. And D, if we add solid sulfur, we will shift away. Oop, no, we won't, because the solid isn't part of the equilibrium mixture. Therefore, there will be no shift. When you have an all gas equilibrium and you decrease the volume, the equilibrium will shift towards the side. This is very important, towards the side with the smallest number of moles of gas. So if we decrease the volume of this system, we will shift towards the left. The corollary is also true. If you increase the volume, you will shift towards the side that produces more of the gas. So a decrease in volume, shift towards the smaller number of gases. And that makes sense because if we decrease the volume of a gaseous equilibrium mixture, we're essentially doubling the concentration because we've removed that extra space, and increasing the concentration increases the number of times the molecules will interact. So decreasing the volume will shift towards the production of the fewer moles of gas. For each reaction, predict in which direction the equilibrium will shift when the volume of the reaction vessel is decreased. Well, remember, if we're going to decrease the volume, we will shift towards the smaller number of moles. So here we have 1 mole of gas, and here we have 2. So this will shift left. Here, I'm only looking at the gas. I don't care about the solids. I have 3, I have 2, so this will shift to the right. Here, I have 2 moles of gas on both the reactant side and the product side, so this will be no shift. Now, when you change a volume or a concentration, you're not changing the equilibrium constant. The equilibrium constant is a constant. As soon as you change the temperature, however, you alter the value of the equilibrium constant. It's only a constant at a constant temperature. When you change the temperature, you change the constant. So if it depends on which side of the equation your heat lies. If you have a delta H that is positive, that means the enthalpy of the product is greater than the enthalpy of the reactant. So you must have heat on the product side or on the reactant side. So if you treat heat as if it was a compound. So if you increase the heat, if you increase the amount of heat, you're adding heat, you will shift away from the addition. So for any endothermic reaction, heat is a reactant. You need heat in order to convert your reactants to products, and your delta H is going to be greater than 0. It's positive. So as you add heat, you shift the reaction towards the product, and then the Kc is going to increase. If you remove heat from an endothermic reaction, the reaction will shift towards the production of reactants, and your product constant K will decrease. But for an exothermic product, heat is produced. It is a product, and your delta H is going to be less than 0. This part right here should be review from Chem 1. If it's not review for you, you need to look at Chapter 10. Now, adding heat will shift the reaction towards the reactants. Remember, you treat heat as if it was one of your compounds, and if you add that, it will shift away from the addition. Now that decreases your Kc. If you remove the heat, so if you cool it off, then you will shift towards the production of products and you will increase your Kc. Now remember, that all makes sense because when we're looking at our Ks, we're looking at the ratio of products to reactants. If I increase my products, I increase my K. If I increase my reactants, I decrease my K. So the key points for Chapter 15, the whole concept of equilibrium, I think is fairly easy for our Chem 2 students to see. We're trying to reach a steady state where there is no net reaction occurring. There are reactions occurring. This is a dynamic state, but there is no change in concentration. We talked about the reaction quotient. Okay, the reaction quotient is the K value, where you have your concentration of your products raised to your appropriate exponent, if required, divided by the concentration of the reactants. Now the equilibrium constant and the equilibrium expression, that's this business here. And we can calculate those equilibrium constants. We can look at the magnitude of the equilibrium constant and relate that to whether or not it's going to be a product's favored reaction or a reactant's favored reaction. And that also helps us to see some spontaneity. Now we can look at spontaneity with our Gibbs free energy as well. And we can predict the direction of the reaction. Now remember the relationships between your delta G and your delta G naught and your K. There are calculations to be had there. Your heterogeneous equilibria was if we have some things that are solid, some things that are liquid, some things that are aqueous, some things that are gas. Remember, solids and pure liquids do not enter into the equilibrium expression. Now we can also use these equilibrium expressions to solve problems. We can calculate all sorts of things left, right, and center. The take-home and of course Le Chatelier's principle, which is what your lab is based on for this particular unit. Now what you need to take with you for the next unit, however, is calculating equilibrium concentrations. So predicting Le Chatelier's principle is typically the real easy part for our Chem 2 students, but it's getting those equilibrium expressions and calculating the equilibrium concentrations that people tend to gloss over, and that's really the part you need to take with you to the next unit. If you have any questions regarding any of these topics, please let me know.